Hello, future engineers, subscribers, viewers, and students. Here is another lecture video in Algebra 5. And here I'll discuss theory of equations, quadratic equations, and worded problems in one variable, particularly in topics number relations, mixture problems, investment problems, and money problems. So first, let's have theory of equations. The number of roots of an equation is equal to the degree of the equation. And I hope that you know that. If the degree of the polynomial is 4, then expect 4 roots. These roots may be real numbers, or it may be imaginary numbers or irrational numbers. And we have to know the principle when we have irrational numbers and complex roots. We must know that they are complex conjugates. So if the roots of polynomials are complex numbers, then they are conjugates. So meaning to say, if one root is 2 plus I, the other root is 2 minus I. If one root is I, the other root is definitely paired with negative I. So another thing, if one root is 1 plus square root of 3i, or 1 plus I square root of 3, then the other root is 1 minus I square root of 3. So as I said, they are complex conjugates. If one root of a polynomial is an irrational number, let us say a plus b square root of c, then another root is definitely a minus b square root of 3. So note of this principle so that we can predict the polynomial given the roots. Then we have Descartes' rule of signs to find the number of positive or negative roots of p of x. So the number of positive roots is the number of variations in signs in p of x. So the number of positive real roots of a polynomial p of x with real coefficients is 1. It is equal to the number, the same as the number of variations in signs of p of x, or less than the number of variations of sign of p of x by a positive even integer. So meaning to say, based on this test, after we count the number of variations in signs, and let us say at the start there are 7 variations in signs in the polynomial, then the number of positive roots would be 7 or 5. Why or 5? Because of this, less than the number of variations of signs of p of x by a positive even integer. So 7 or 5, because the other two roots may be complex conjugates. That's the meaning of that. Then another pair of complex conjugates, and so on and so forth. So 7 or 5 or 3 or 1. So keep on subtracting positive even integer or 2. If the number of variations in sign of p of x is 4, then there will be expected 4 positive 4 roots, positive real roots, or 2, and minus 2, or none at all, because all the 4 roots may be complex conjugates, 2 pairs of complex conjugates, or the other 2 may be negative. So that's why it is also possible that there will be no positive real roots of the polynomial. So 0 can also be possible. Then the number of negative real roots of a polynomial P of x with real coefficients is, so the same principle here, the same as the number of variations of sign of P of negative x, or less than the number of variations of sign of P of negative x by a positive even integer. So another illustration, if after we count the number of variations of signs in of P of negative x, then let us say it is 3, then the number of negative roots would be negative would be 3 or 1. If the number of variations in signs of P of negative x is 5, then the number of negative roots would be 5 or 3 or 1. So that's it. That's the principle. Then let's have quadratic equation. The general quadratic equation is ax squared plus bx plus c equals 0, right? So let's derive the quadratic formula. First, we divide everything by a, and we have x squared plus b over a times x plus c over a equals 0. Let us complete the square in these first two terms, then transpose c over a to the right. To complete the square, we add the square of 1/2 the coefficient of x, the first degree term. Like, for instance, x squared plus 4x plus 4 is a perfect square trinomial. So to complete the square, if we have x squared plus 4x, we have to add square of 1/2 coefficient of x, which is 4. So 1/2 of 4 is 2, and 2 squared is 4. That's why x squared plus 4x plus 4 is a perfect square trinomial. So in this case, we add 1/2 of b over a quantity square, and we also add the right side to balance the equation, to maintain the equation. So complete the square in x. So we have x squared plus b over a times x plus 1/2 b over a quantity square equals b over 2a, or 1/2 of b over a quantity square, which is we added in the left side, so also add up in the right side, and we have negative c over a after we transpose this to the right. So this is now a perfect square trinomial, and we can write this as x plus b over 2a quantity square, and let's simplify the right side as b squared minus 4ac all over 4a squared. So we expand and simplify. Then we have x plus b over 2a quantity square equals b squared over 4a squared minus c over a. And of course, simplifying further the right side, that's b squared minus 4ac all over 4a squared, where 4a squared is the LCD. So LCD for a squared in the right side. So we divided by 4a squared, so b squared, then minus 4a squared divided by a is 4a, so minus 4ac, then all over 4a squared. So x plus b over 2a quantity squared equals b squared minus 4ac all over 4a squared. Then we extract the square root, then we have x plus b over 2a equals plus minus square root of b squared minus 4ac over 2a. So plus minus square root of quantity b squared minus 4ac all over 2a. We now have the quadratic formula, which is, after we transpose this to the right, negative b plus minus square root of b squared minus 4ac all over 2a, because 2a is common. So extract the square roots. So that's the result. Then we now have the quadratic formula, which is x equals negative b plus minus square root of b squared minus 4ac all over 2a. So this is the quadratic formula. Then in this quadratic formula, the roots are negative b plus square root of b squared minus 4ac over 2a, and the other root, x2, is negative b minus square root of b squared minus 4ac all over 2a. So one root is negative b plus, use plus in this radical, square root of b squared minus 4ac over 2a, and the other root is x2 negative b minus square root of b squared minus 4ac over 2a. Therefore, from here, if we add these roots, then we can eliminate the radical part, and we have negative b plus negative b, which is negative 2b all over 2a, and that simplifies to negative b over a. The sum of the roots, therefore, is negative b over a, and you have to remember that. Then the product of the roots, if you have this conjugates, so it is negative b quantity square, which is b squared, then minus quantity, the radical sign is removed. So negative b quantity square is b squared, then minus, because we have plus and minus here, minus quantity b squared minus 4ac all over 2a squared or 4a squared. Since we can eliminate b squared, then we have negative of negative 4ac. So the product of the roots would be 4ac all over 4a squared. I hope that you can follow. So 4a squared, 4ac over 4a squared, and this simplifies to c over a. The product of the roots, therefore, x1 times x2 is c over a. Because of this, this leads us to the formula which I call Stillhat's formula. You may follow or you may not, that the quadratic equation can also be written as x squared minus the sum of the roots times x, then plus product of the roots equals 0. So this is the formula. X squared, interpret it, minus sum of roots times x plus product of roots equals 0. So in general, from the general quadratic equation, ax squared plus bx plus c equals 0. If we divide through by a, then it reduces to x squared plus b over a times x plus c over a equals 0. And I interpreted that as x squared minus sum of roots x, because sum of roots is negative b over a, so negative of negative b over a times x, which is the positive b over a. So that's correct. Then the third term is c over a, which is the product of roots, which is this, and equals 0. So that's the interpretation of the quadratic equation. Then we have here the nature of roots of a quadratic equation as described by its determinant. The discriminant of the quadratic equation is the radicand in this here, in this radical, so b squared minus 4ac. So that's the discriminant. Then the nature of the roots will depend on this discriminant. So if the discriminant is positive, so we have two distinct real roots because of square root of positive. When b squared minus 4ac is greater than 0 or positive, the roots are real and distinct. So if it is irrational, then as I said, they are negative b plus that square root over 2a, and the other root will be negative b minus that radical over 2a. So that's why you have to recall in the first part about that principle. So if one root is irrational, then there is a pair of root which is also irrational. So for instance, one root is 1 plus square root of 2. The other root would be 1 minus square root of 2. That's the meaning of that. Then when b squared minus 4ac is exactly equal to 0, that there is only one root that is repeated. And it is a perfect square trinomial. The quadratic equation is a perfect square trinomial. Let's verify that x squared minus 6x plus 9 is a perfect square trinomial. X minus 3 quantity square, right? If you're going to, the root is 3 and it is repeated. If you're going to evaluate b squared minus 4ac, it is 0. So b squared negative 6 squared is 36. Minus 4 times 1 times 9. So 4 times 1 times 9 is 36 also. So negative 6 squared minus 4 times 1 times 9, which is minus 36 equals 0. So that verifies that or a perfect square trinomial, the discriminant is 0. And lastly, when b squared minus 4ac is less than 0 or negative, then we'll have complex conjugates as roots. So that testifies that the principle earlier stated in the first part, that if one root is I, the other root is negative I. If one root is 1 plus 3I, the other root is 1 minus 3I. If one root is 2 minus square root of 5I, or 2 minus I square root of 5, the other root is 2 plus I square root of 5. So I hope that the principle is clear. Then we have to proceed with the principles on the worded problems, and one-word problems will be about number relation problems. You may encounter problems such as the sum of positive or the sum of positive odd or even integers, and they may be represented algebraically by x, the lowest integer, x plus 2 plus x plus 4, or x minus 2 plus x plus 2. So these are the representations for that statement about number relation problems. Then another one, the number is 24 more than 1/3 its value. If the number is represented by x, then the interpretation is x is equal to 1/3 of x plus 24. It should not be interpreted as 24 plus 1/3 of x, although they are the same, because of the usual algebraic transformation of that statement. The correct way of translating this to English from this algebraic statement is x. If x is the number, then x is equal to 1/3 of x plus 24. Then we have mixture problems. In mixture problems, the pure amount of substance in that mixture is obtained by multiplying the product of the concentration and the total amount or the content. So for instance, if you have a mixture of pure milk of 80 milliliters and hot water, which is 20 milliliters, the total amount in the mixture would be 80 plus 20 is 100 milliliters. Then the concentration of milk in that mixture is 80 milliliters divided by the total amount, which is 100 milliliters times 100%. So that, therefore, the concentration of milk in the mixture is 80% pure milk. So I hope that it is clear. So the pure amount of a substance in a solution is obtained by multiplying the content, the amount, by the concentration of the substance. So if two or more substances of different concentrations are added, the concentration may be 0 if the other solution does not mention the pure amount in the first solution, so concentration may also be 0. So let us say this is the first solution with concentration C1 and the amount is X, then to be mixed with another solution with concentration C sub 2 and amount Y. If you add the two, the result will be X plus Y for the total amount. But the resulting concentration is denoted by C. And the principle above should be used. So we are actually equating the pure amounts in these two solutions. This is C sub 1 times X plus C sub 2 times Y to the pure amount in the final solution. If the resulting concentration in the final solution is C and the total amount is X plus Y, then it would be the pure amount in the final solution would be C times quantity X plus Y. So the concentration is C, the total amount is X plus Y. So C sub 1 times X plus C sub 2 times Y equals C times quantity X plus Y. Take note that in this equation, we are equating pure amount of substance in the first solution and the pure amount of substance in the second solution. If we are talking about alcohol solution, for example, hydrochloric acid. So pure amount of hydrochloric acid in the first solution plus pure amount of hydrochloric acid in the second solution equals, this is the resulting solution, then this would be the total amount. So the pure amount in the final mixture would be C times X plus Y. We then proceed to investment problems because the formulas and principles with mixture problem is the same. So the net interest obtained from two or more business ventures is equal to the sum of the interest obtained from each business venture. So that is, since interest is principal rate of simple interest times time, which is denoted by Y here in order not to confuse. Y is taken 1 year in algebra, although in engineering economy, that may take any time. It may be less than a year, days, weeks, and so on, or in years. But in algebra, problems here, time is taken 1 year. So that's why interest is simply principal or capital times rate of simple interest times 1. So it reduces to PR. So adding interest, this is the resulting interest, the total principal times the resulting net interest R. So it would be equated to the interest earned in one line of business, then interest earned from the second line of business, and so on and so forth, depending on the number of businesses. So P sub 1 is principal or capital in the first line of business. R1 is the rate of simple interest earned or realized in the first line of business. Then money problems, all you have to do is understand the statement of the problem involving money and hoping that you can translate that English statement to algebra for the success of its solution. So the principle will just be problems involving money requires pure analysis and principles in algebra and formulating equations. So that's it. For the next slide, we'll have problem solving. So let's have problems for solution. The first problem, find all roots of x to the fourth plus x cubed minus x squared plus x minus 2, given that I is a root. Since your calculator is capable of finding the roots of up to 4 degree, then you can actually use your calculator. But I'll present here a solution because the calculator allowed before is only for third degree up to third degree polynomial. So I'll just apply the principle here. So if one root is I, the other root is negative I. Remember that. So plus minus I are roots. Therefore, if we write this in factored form, representing plus minus I, it would be x squared plus 1. So that x is plus minus square root of negative 1, which are plus minus I. Then having expressed the roots plus minus I in algebraic factored form, which is this, then we can divide this given polynomial to find the other roots. By long division, so we write the polynomial, then we divide it by x squared plus 1 to determine the quotient. So x squared plus 1. So x to the fourth over x squared is x squared. Then x squared times x squared is x to the fourth. X squared times 1 is x squared. We put it under the term with the same degree. Then we subtract So of course, x to the fourth is eliminated. Then we bring down x cubed. Negative x squared minus x squared is negative 2x squared. Let's bring down x and negative 2 also. So x cubed minus 2x squared plus x minus 2. This is the new uh, dividend. So x cubed divided by x squared is x plus x times x cubed, x times x squared is x cubed under x cubed, x times 1 is x, so put it under the term like to it. Then we subtract again, we can eliminate x cubed, we can eliminate x, so what remains would be negative 2x squared minus 2 after subtracting. Then negative 2x squared divided by x squared is negative 2. Negative 2 times x squared, negative 2x squared, negative 2 times 1, negative 2. So since they are like, after we subtract, the result would be 0. So this is the quotient, and we write this in factored form as x plus 2 times x minus 1. So you have to check if the expression is this binomial is factored correctly. So that's the correct factored form. Therefore, the other roots are negative 2 and 1 after we equate this to 0. So negative 2 and 1. Therefore, the answer would be plus minus I and negative 2 and 1. Those are the roots. We then proceed to the next problem. Find a polynomial of lowest degree with rational coefficients that has 2 square root of 3 and 1 minus I as roots. So based on principle, that polynomial would be, the lowest degree of that polynomial would be 4. Because we pair this with, by principle, when we have irrational factors, we pair this with 2 minus square root of 3. Remember the principle? And for this root, which is complex, they are complex conjugate, so the other root is 1 plus I. So adding 2 more roots, then the degree, the polynomial of lowest degree would be 4th degree polynomial. So writing it in factored form, x minus quantity 2 plus square root of 3 for this, and the other root is 2 minus square root of 3, so x minus quantity 2 minus square root of 3. Then for this root, x minus quantity 1 minus I, and because the other root is 1 plus I, so in expression, it is x minus quantity 1 minus I. So simplifying, this is x minus 2 minus square root of 3. This is x minus 2 plus square root of 3. This is x minus 1 plus I. And this is x minus 1 minus I. So we have x minus 2, negative square root of 3, positive square root of 3, which can be simplified into x minus 2 square minus 3. Then this one, x minus 1, then plus I, negative I. This can be simplified internally as x minus 1 square, then negative I square. Since I square is negative 1, negative of negative 1 is positive 1. So this is x minus 1 square, then plus 1. So again, p of x is x minus 2 square minus 3. Then the other one is x minus 1 square plus 1. Expanding this, so we have p of x equals quantity x squared minus 4x plus 4 minus 3, then times quantity x squared minus 2x plus 1, then plus 1. Simplifying further, this is p of x is x squared minus 4x plus 1 times x squared minus 2x plus 2. Then let's expand x to the fourth, x squared times x squared. Then we have negative 2x cubed. Then we have positive 2x squared. Then negative 4x to be distributed to each term here. Negative 4x times x squared, negative 4x cubed. So put it under this term, like term. Negative 4x times negative 2x is positive 8x squared. Put it under this. And negative 4x times 2 is negative 8x. Then 1 times quantity x squared minus 2x plus 2 would be the same, x squared minus 2x plus 2. So put x squared here, then negative 2x here, then plus 2. Then simplifying, combining like terms, the polynomial therefore is x to the fourth minus 6x cubed plus 11x squared minus 10x plus 2. So that's the polynomial of lowest degree given these two roots. So the other roots are correspondingly 2 minus square root of 3 and 1 plus I. So this is the answer. And lastly, what's the answer? And lastly, without solving, determine the number of positive real roots in the polynomial p of x equals 6x to the 6 minus 5x to the 4th plus 3x cubed minus 7x squared plus x minus 2. How about the number of negative real roots? So remember the principle, the number of positive real roots is equal to the number of variations in signs less by a positive even integer. So let's count the number of variations of signs of p of x. So from positive, it becomes negative. So therefore, this is the first variation in sign, second variation in sign, third variation in sign, fourth variation in sign, so fifth variation in signs. Therefore, the number of positive real roots is 5 or 3 or 1. So number of positive roots is 5 or 3 or 1. Then for the number of variations, the number of negative real roots, so we replace x by negative x. So 6 times negative x to the 6 minus 5 times negative x to the 4 plus 3 times negative x cubed minus 7 times negative x squared plus negative x minus 2. So this simplifies to p of negative x is 6x to the 6 minus 5x to the 4th minus 3x cubed minus 7x squared minus x minus 2. So if we count the number of variations in signs, this is the first, and it does not change anymore. The sign do not change anymore. So there is only one variation in sign for this. So that means we expect one negative real root. So the number of negative real roots is 1. So that's it for this video. I hope that you were able to follow the explanations and you are prepared to solve problems of this kind also.